Dampness in Buildings and Diagnosis, Module 11. Long-term assessment of atmospheric moisture and the internal environment. There's some atmospheric moisture, perfectly visible as clouds. But in the internal environment, you don't see it like that. It's simply clear, nothing effectively to be seen, except possibly the consequences of it. So how do we do long-term monitoring? Well, these are temperature and relative humidity data loggers. They'll record the temperature, relative humidity and the dew point over a period of time. Data direct from the logger, that's with its own software. See the temperatures, dew point and humidity. We can also convert the data to vapor pressure. And of course this is directly related to the moisture content of air. So when we compare internal moisture levels with those externally, as we found earlier, it becomes the differential or excess vapor pressure. And it's very useful because it can be used as a guide to ventilation and or moisture production by the occupants. So how do we place the data loggers? Well, very easy. Indoors, keep them away from heat sources such as radiators and lamps and fires. Keep them away from windows and try to keep them over 15 centimeters away from a wall surface and place them where the airflow is not restricted. Also, externally, try to keep them away from direct access to elements such as rain, snow, etc. Position to allow good typical airflow. And I've always found that the simplest protection against all these is a polystyrene cup with a data logger hanging in it like a bell clap and sealing the logger in it via the piece of string. However, with a data logger, you may collect anything between sort of 500 and 2,000 bits of data. In this case, we were collecting it at half-hourly intervals. So sticking to something like a psychometric chart will take you a month of Sundays. The easiest way is to use a spreadsheet that's already set out. One simply puts the data into the spreadsheet and all the calculations are done for you. And we put in here the temperature and relative humidities. It's just an example of bedroom 1, and it automatically works out the vapor pressure and the differential vapor pressure. It's quite interesting to look at vapor pressures. This is the summer of 2010, good ventilation. Note in the middle there is the green line. This is what I would loosely call the neutral point. It is the balance between water inside and water outside. It's so-called neutral. And on this you can see during the warmer months of the year, on average there's as much water in the house as there is outside. It's only as the months get colder, I'm here specifically looking at September, when we start shutting windows, that our differential vapor pressure on average starts to increase. We are now cutting down the ventilation. But with windows mostly open, during the summer months, there is no real difference between internal and external vapor pressures. But one can see that these vast variations can occur all the time, up and down, something like a yo-yo. But on average, that's the sort of result we'll get. Changing internal occupation, another job, there it is on the left. The 0 point, there's much water vapor inside as outside, and above that there's more water vapor in the building. Differential vapor pressure, occupied, unoccupied. What happened here was quite simply the first decline around about the 15th of March was simply they went away for a weekend, so we had no internal moisture production. They came back, we started to get pretty high internal moisture production as indicated by the differential vapor pressure. Then they went away for a long weekend, and in fact it virtually dropped again to nothing, and then when they came back it started to climb. So it does show you what is actually produced by occupancy. Another problem that arose was a kitchen with mold in the cupboards, and that's the actual data from the data loggers. And note the very high relative humidity in the cupboard where there was mould, and the very low temperature. So it was thought that there was dampness coming off the wall with the cupboard doors shut. However, when we converted those to differential vapour pressure, there's the same amount of water in the cupboard as there was in the kitchen. The mould was simply due to the colder condition and hence greater relative humidities developed within the cupboard. Looking at a database which was made up of conditions found in normal non-problem houses, and this has been used as a baseline, this suggests a differential vapour pressure of up to around about 0.45 to 0.5 kilopascals might, or rather could, be regarded as acceptable during the colder months of the year, indicating perhaps sufficient ventilation. Remember, differential vapour pressure compares the internal moisture levels with those externally. It's a measure of moisture production and/or ventilation. However, if you think about it, when one is dealing with internal conditions, in many respects, it's effectively relative humidity that is the major factor. Why is this? Because it potentially leads to health problems, especially related to dust mites, mould, bacteria, viruses and so forth. That is what we refer to, in essence, a damp environment. That's what's caused these problems. Nevertheless, it's still very important to provide and look at differential vapour pressures because they provide a guide in relation to the ventilation and/or moisture production, and this is especially useful where problems are encountered. Importance of relative humidity? Well, mould can grow on some certain moisture sensitive materials by maintenance of relative humidities as low as 75 to 80%. Some require higher humidities or condensation. Given the surface temperatures of walls, especially behind cupboards, these are inevitably several degrees lower than the room temperature. In this case, the relative humidity in the boundary layer of air against such surfaces will be in excess of 5 to 20% higher than that in the room. So here we have a room at 50% RH on the left. That air comes into contact with a cold wall of 14 degrees. The air is cooled by the coldness in the wall, and the relative humidity rises to 80% in the boundary layer of air against that wall. Hence, we have conditions suitable for certain moulds. Similarly, in a cold environment, that also leads to a higher relative humidity under what one could call normal airborne water levels. We saw this in the case of the cupboard earlier on. So it's important to note that in a cold environment we can raise the temperature, and this will reduce the risk of these problems as it will lower the relative humidity. Again, simple bottom, go into a property, it's very cold, 80% relative humidity, put some heat on, drop the relative humidity to 50% if we can get the heat up to 20 degrees. We can also monitor wall surface temperatures in the long term, done by these little gizmos, or these are the ones that are easily available and they're not expensive, eye buttons. They're about the size of a penny, they look like a watch battery. Fix them to the wall, flange side down, and on the bottom diagram is the kit that is used to get the data off these. And one thing one does certainly find is that the surface temperatures follow very rapidly and relatively closely to air temperatures. However, look at the bottom diagram, and this even shows it where we're using intermittent heat. The change in surface temperature is quite rapid in relation to the air temperature. And this is shown up in a real-world example. Here we have internal surfaces and internal air temperatures. They're the top two lines. The bottom two lines are the wall surfaces. And one can see the arrows mark this As the air temperature goes up, so does the wall surface. As the air temperature goes down, the wall surfaces go down. It's pretty rapid, this relationship between internal air temperature internal air temperature and the wall temperature. And if we look at this in another way, internal wall surfaces and external air, the influence of external temperatures is much slower and in longer term than the air temperature. Short term, internal surfaces follows the air temperature, thus in long term, internal surfaces overall slowly follow external air temperatures. And again, we can see this on these two graphs, following the wavy lines that go along. It's much slower and longer term than the internal air temperatures. Surface temperatures and dew point on furniture. It's quite an interesting one, this. We monitored the wall behind a sideboard and the back of the sideboard, the surface temperatures, did the calculations, and what we found was that the wall behind the sideboard was dropping into condensation, as we can see from the graph there, quite periodically. However, the back of the sideboard, which was simply a couple of inches away, never went into condensation. However, that was the item that had mold growth on the back of it. So there was mold growth there, no condensation. The other feature with reference to airflow, it can be improved behind objects. The air temperature influencing the surface temperature. Here was some furniture against the wall. It was very cold outside and been so for a few days. Surface temperature of the wall shown to be about 18, but the cold area where the furniture had been was only 10. This was simply because there was no airflow and we had no heat input from the air. However, take these away and the internal air temperature now influences the surface and not the coldness in the wall. So moving the furniture allows the old stagnant air flushed away and replaced with circulating warmer air. Thus the risk of condensation and mold growth will decline. Air temperature, therefore, and associated circulation plays a very important part in warming up the surfaces of walls. This should not be underestimated. Raising surface temperatures reduces the risk of surface condensation and high relative humidities developing in the boundary layer of air. Thus, we can reduce the risk of surface condensation and mold growth on such surfaces. Even if we take a normal property per se, there are variations, especially in corners and bases of walls, in surface temperatures. And here's one example. In this case, it's the same house. In the downstairs, at one time it got up to 21 in the corner at the on the surfaces, but on the bottom it went down to 11 degrees. In essence, the wall at the base of a building can act as a thermal bridge from the cold ground. The other beauty of monitoring, it can identify intermittent problems, and in this case it was condensation during the night. So here's just an example of what was happening. Occupation on the bottom and wall surface temperatures. We've got occupation and heating at the bottom, then occupation and heating off, and occupation and heating on in the morning. And if we look at the wall surface temperatures, they go up and down according to the actual time of occupation in that particular room. If we then start monitoring atmospheric moisture, we find that goes up and down. Obviously, when they're in the room, they're going to start generating moisture. That will dissipate when they leave the room and start building up again, say, next morning. And if we look at this data roughly, or the principle of this data that was obtained, we found that condensation was occurring in the early hours of the morning before the atmospheric moisture totally dissipated, whereas the wall surface temperature was dropping quite rapidly. So this is the sort of thing that long-term monitoring will pick up It can pick up, it did in this case, the problem was occurring early in the morning. That is the end of dampness in buildings, end of module 11.